This is the second lecture of systematic analog CMOS circuit design using the GM over ID technique. Device characterization. On this lecture, we're going to discuss how to actually characterize a device. We'll extract key parameters like current density, ID over W, GM over ID, GM over GDS, and transit frequency, FTT. We do this so we can create our own lookup table. For this session, we're using LTspice. It's free and easy to find online. Our focus is a 45 nanometer process node. But don't worry too much about that detail. This method works for any process node and with any simulator, whether you're using LTspice, Cadence Virtuoso, or others. The most important thing is to grasp the method, not just the particular tools. We will start characterizing the N-channel MOSFET. As discussed in the first lecture, the one very good thing about GM over ID is that it is linked to other figures of merit, such as GM over W, ID over W, GMR0, the intrinsic gain of the transistor, and the transit frequency. We will extract these parameters or figures of merit, and, therefore, create our lookup table. We will characterize the device by sweeping it in 4 dimensions: the device length, the gate-to-source voltage, the drain-to-source voltage, and the source-to-body voltage. We start with the GM over ID. Take note that we are doing this with a 45 nanometer process. To extract this parameter, we first bias the gate voltage of the NMOS with a DC voltage. Similarly, we provide the drain of the NMOS with a DC voltage. We also set a reasonable width and length for this process. For width, we give it 5 micrometers and 0.5 micrometers for its length. For simplicity, we set the source-to-body voltage, VSB, to 0 volts. By definition, the transconductance GM is the change of ID with respect to the change in VGS, or GM is equal to delta ID over delta VGS. To get the GM, we perturb the gate voltage with a small amplitude sine wave. We select a reasonable amplitude to be 20 millivolts here, and its frequency to be 1 kilohertz. By doing this, its drain current will also be perturbed. The drain current now is its DC value ID plus delta ID. By dividing the change in ID with respect to VGS, we get the GM. By dividing the GM we just obtained by the DC drain current, ID without perturbation, we get GM over ID. By sweeping the channel length L, the VSB, VDS, and VGS, we are to produce multidimensional plot. To simplify our discussion, we will only be sweeping the parameters VGS and VDS in our LTspice simulation. We will leave it as an exercise for the student to sweep L and VSB. A reasonable value for VGS is 0.2 volts to 0.9 volts, because this range covers the below threshold or sub-threshold region, and also includes VGS values greater than the typical VTH value of 0.7 volts. Similarly, for VDS, The drain-to-source voltage range from 0.2 volts to 0.9 volts covers the typical voltage headroom allocated for a transistor in analog ICS. We summarize in this slide the step-by-step method for extracting GM over ID. We show on this slide the schematic and netlist code in LTspice for the test bench setup. We also show on this slide a step-by-step procedure that the student can follow to extract the GM over ID. This is the GM over ID with respect to VGS at different values of VDS. You can see that GM over ID almost does not change even when VDS is swept from 0.2 volts to 0.9 volts. The length here is maintained at 0.5 micrometers for simplicity. Next is the GM over GDS, or the GMR0, the intrinsic gain of the transistor. The output conductance, GDS, is defined as the change in drain current ID with respect to the change in VDS. We perturb the drain voltage with a small amplitude sine wave. We chose 20 millivolts as the amplitude here and obtained the corresponding change in drain current. Shown on the right is the plot of ID when VDS is perturbed. We divide delta ID by delta VDS in order to get the output conductance GDS. Then, just divide GM by GDS to get the parameter we want. Also, for simplicity, we only sweep VGS and VDS. We leave it as an exercise for students to sweep VSB and length. Here, we summarize the step-by-step procedure to get GM over GDS. This is the LTspice netlist code and schematic to obtain GM over GDs, while sweeping the DC voltages VDS and VGS of a 45 nanometer NMOS. This is GM over GDS while sweeping VGS and VDS. The length here is maintained at 0.5 microns, and the source-to-body voltage VSB is set to 0 for simplicity. Next is the transit frequency. To get the transit frequency, we must first get the CGG, or the total gate capacitance of the NMOS. Capacitance is defined as the charge per unit voltage. The charge we are interested in is the charge at the gate terminal of the transistor, CGG. It is equal to the product of the change in gate current, delta IG, times the time difference, delta T, where the change in gate current occurred, over the change in gate voltage, equivalent to delta VGS. GM, as discussed previously, is delta ID over delta VGS. Transit frequency is GM over 2 pi CGG. We need to perturb the gate voltage by a sine wave with an amplitude high enough so that LTspice can interpret the very small changes in gate current, delta IG. We select 100 millivolts as the amplitude of the sine wave used to perturb the gate terminal. Again, we only sweep the DC voltages VDS and VGS for simplicity. The student can try sweeping the length and VSB on their own. Here, we summarize the step-by-step procedure to get transit frequency. We show here how we do it in LTspice. The student is encouraged to study the test bench and LTspice code on their own. This is the transit frequency FT, measured while sweeping the VGS and VDS. The length here is maintained at 0.5 micrometers, and the source-to-body voltage VSB is set to 0 for simplicity. We now discuss obtaining the current density, ID over W. For this one, we just need to sweep both VDS and VGS. Get the corresponding ID for each VDS and VGS. Divide ID by the width set, 5 micrometers. That's how we get the current density. The student is encouraged to try sweeping the length and VSB on their own. This is how we do it in LTspice. The student must study the LTspice code and the schematic on their own. This is the current density ID over W, while sweeping VGS and VDS. The length here is maintained at 0.5 micrometers, and the source-to-body voltage VSB is set to 0 for simplicity. PMOS device characterization. Characterization of PMOS is the same as NMOS, except the connections are inverted, as shown. The same concept is applied. This is the GEM over ID setup. The student is encouraged to study them on their own. This is the LTspice netlist and schematic for getting the GM over ID PMOS. This lookup table is for the GM over ID of PMOS. This is the GM over GDS setup for PMOS. The student is encouraged to study them on their own. This is the LTspice netlist and schematic for PMOS GM over GDS. This is the lookup table for the GM over GDS of PMOS. This is the transit frequency generation setup for PMOS. The LTspice netlist and schematic for PMOS transit frequency. This is the lookup table for the transit frequency of PMOS. This is the LTspice netlist and schematic for PMOS current density, ID over W. This is the lookup table for the current density of PMOS for different values of VGS and VDS.
End of the lecture.